Okay, so good day everyone. For this video, we are going to have another example. We will try to prove the logical equivalence of P or not Q and not P or not Q with not Q. Okay, so we will be using still the laws of logical equivalence. So what can we do here? So one technique that you can first do is to look for something common between the two na group na statements. So we can see here that there is something common, the not Q. Okay, so let us try to change the position of not Q or P and not Q or not P. Okay, so we are using the what? Commutative na laws. And now we can see that we can use a distributive na law for this one. We have the not Q, and they are both being connected by the or na operator. Okay, so let us try. We have the not Q or P and not P. Okay, we are using the distributive na law. Again, you can do that because we have the not Q on both of the group na statements, and they are both being connected by the or na operator. Okay. Now, the not Q or, and this is can be evaluated into what? This can be evaluated into false by using the negation law. Okay, so P and not P will result to false. Now, not Q or false will result to not Q using the identity na law. Okay. Now, let's move on to another example. We have P or P and Q is logically equivalent with P. So is this familiar to you? So P and P or of grouped P and Q is actually the what? This is actually the absorption law. But we will prove this using that this is indeed correct using the laws of logical equivalence. So at first look, it is quite different to deduce how it was done, right? But this P could actually be further used with other na connectives. So we can use of the identity na laws. So we can use P and true or P and Q. Note that P and T will is logically equivalent to P or by itself. Okay, so we can now make use of distributive na law. Okay, you know that we have both P on the both sides and they are both connected by the and, right? So P and true or Q. Okay, so just writing down the laws that we used here, we used the identity law. And in here, we use the distributive na law. And reverting this back to its old na form, so we have P and T or Q, right? So P and distributing that to T, so P and T. Then copying this. So we have or and distributing again P and to Q. So we have P and Q. And that reverts back to this form. Okay. So moving back, So we have P and T or Q. So this can be evaluated into what? This can be evaluated into true, okay, using the domination na law. Okay, so this is the domination na law. So any variable that is taking the disjunction with any true value will be true. Because by the law of OR na operator, right? If there is a true, it will result to true. Okay? So now P and true will be true using the identity na law. How is that the case?